Before we get into the vectors and planes in the title of this video here, I want to make sure we're cool with the notation and the concepts. R of t is a curve. It's written as a vector, R with a little arrow on top, but the tips of those vectors trace out a curve. R prime of t is the tangent vector to the curve, and it gives the direction of the tangent line. I just realized I should be putting periods at the end of my sentences. T of t, which is given by r prime of t divided by the magnitude of r prime of t, is the unit tangent vector. That is to say that the magnitude of t is equal to 1. Okay, so that's a recap of our symbols, because we're going to have some new ones. The vector that is orthogonal to the unit tangent vector t that has length 1 is the unit normal vector. It's denoted by an uppercase n, and I'll write it as n of t, and it is equal to the vector t prime of t divided by the magnitude of t prime of t. It's a unit vector with length 1 because it is a vector divided by its own magnitude, and n is orthogonal to t because n is a scalar multiple of t prime of t, and since t is a unit vector, its derivative is orthogonal to it from previous work that we've seen. Well, I think this video is called two vectors, and so here's the other one. The unit vector orthogonal to both t and n is the binormal vector. I know. I'm thinking it's binormal because it's normal to two vectors. B of t is how it's denoted, uppercase B, and it's achieved by crossing t and n. So cross the unit tangent vector and the unit normal vector. We get a vector of magnitude 1 because of the expression that we saw giving the magnitude of a cross product in relation to the sine function. But I really think a visual is in order to understand what's going on with all these vectors. Suppose we have a curve C. A point on the curve is given by r of t. That's a vector in standard position, so its tail is at the origin. Let's mark at the head of r of t a point on the curve, and that'll be the point of everything right now. At the point that's given by r of t, there exists a tangent vector that we're going to say is r prime of t. Parallel to that tangent vector, but of length only 1, is our unit tangent vector. So there's our t of t. T prime is going to be orthogonal to t of t. So there's t prime of t. And n of t is parallel to t prime of t, and it is also a unit vector, and so it has the same length as t of t. Did I pull off the same length there? Give me just a second. Okay, I wasn't sure I believed it, but now I do. Now, this binormal vector is given by t cross n, and so for how this is drawn here, we've got t pointing to the right, n is pointing up, and if I cross t with n, so if my fingers on my right hand are pointing in the direction of t, and then I curl them into the direction of n, then my thumb will be kind of sticking out of the page, or I guess it's the screen, isn't it, toward us. And that's the binormal vector b of t. It is orthogonal to both t and n. Had to figure out how to draw that little right angle there. And as you know, n and t are orthogonal to each other. As we said before, t of t is r prime of t divided by its magnitude. And n of t is t prime of t divided by its magnitude. So again, r of t gives us a point on the curve. Yeah, I know you're tired of hearing it. The tangent vector gives us the direction that a point on the curve would go if the curve broke at that instant. The normal vector is an indication of where the particle on the curve is actually going to go. So the tangent vector points in the direction of current motion, and the normal vector kind of points in the direction of future motion. So what does the binormal vector give us? Well, let's see. The plane determined by t and n is called the osculating plane of C at a point P, that point being the point of everything that we've been talking about here. It contains the vectors t and n, and so it actually has a direction vector that is b. So b is the direction vector of the osculating plane. And now if you imagine this curve in 3 space, it doesn't exist in a plane, but the osculating plane at P is the plane that captures as much of the curve at that point as it possibly can. In other words, the osculating plane comes closest to containing part of the curve near P. It contains what's called the osculating circle at P. It's the circle that holds more of the curve than any other circle can. Here's what I mean. At any particular point on the curve, there's a circle whose curvature is just right to capture, let's see, for that circle, maybe this here? Maybe I need a bigger circle. It captures a portion of the curve. And maybe for this circle, it would make more sense to, ooh, there we go. Oh yeah, okay, here. It's not at the point P, but over here, the curve is kind of captured by this circle, at least in a little neighborhood around a point on the curve. And as you can see, the bigger the curvature, the larger the circle I need in order to capture a portion of the curve. Well, that circle is the thing called the osculating circle. The radius of the osculating circle is given by the Greek letter rho, and it is 1 over kappa, the curvature of the curve. And so the greater the curvature, the smaller the radius of the circle needed to capture part of the curve. And that circle is contained in the osculating plane. That osculating plane has a direction vector of b that comes from crossing t and n. So what is this osculating about? In Latin, the word osculum means to kiss. And so it's the osculating circle is a circle that kisses the curve. The osculating plane is the plane that kisses the curve. Now, I said there were 2 planes in the title of this video, I think is what I said. The other plane that I want to refer to is the one that's determined by b and n. And as you can see, because they are orthogonal to the unit tangent vector, the tangent vector is going to go right through the plane. In fact, it's going to hit the plane at a right angle. The tangent vector is normal to this plane, and that's what the plane is called. The plane determined by b and n is the normal plane to the curve at P. And because it's determined by b and n, it should make sense that its normal vector is t.